If there's any questions on 1 through 8 or any questions in general, happy to start with those. Victoria? 5? Sure. Let's see, let me find it. So we have 4x minus 4y is greater than or equal to negative 16. And then negative x plus 2y is greater than or equal to negative 4. So the first thing that I'm going to do is I'm going to rearrange things so that these are in slope-intercept form. So the first equation, I'll subtract 4x from both sides. And then divide both sides by negative 4. Remember, when we divide both sides of an inequality by a negative, though, the inequality symbol switches direction. And then similarly over here, adding x to both sides, and then dividing both sides by 2. Since here we're dividing by a positive, the inequality symbol doesn't change direction. So far, so good. Then we'll pretend each of these inequalities is an equation, and I'll use that equation to figure out 2 points that would lie on that line. So maybe I pick 0 for x, and when I plug in 0, I get 4 for y. And then maybe I'll pick negative 4 for x. When I plug that in, I get 0 for y. Again, it doesn't really matter which x's you're choosing to use. Same thing here. So maybe I'll plug in 0 for x. I get negative 2 for y. And then maybe I'll plug in 4 for x, and that will give me 0 for y. So there's my points on my lines. So let's graph this stuff then. Let's see, 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I'll graph this one in blue and this one in green. So I have 0, 4. And then negative 4 is 0. And since this was a less than or equal to inequality, I'm going to be using a solid line. And I'm going to be shading below. I'm not going to do the shading right now. I'm just going to draw the little arrow because I really only care about the overlap of the 2 shaded regions. And just for keeping things neater, I'm just going to do only the overlap. All right, let's see. And then I have 0, negative 2, and 4, 0. And I'll draw those. So, oops. I guess I should make that a little longer. Again, I know it's a solid line because this was a greater than or equal to inequality. And since it's greater than or equal to, I'm shading above. So my region of overlap is just going to be this section like in between the two. In between the 2 lines. And that's it. Does that feel okay there, Victoria? Again, maybe a little weird because the intersection is way down there in the 3rd quadrant, kind of far away, but just keep extending stuff as long as you need to get to the, so you can see that intersection and do the overlap. Anybody else with questions from this? Yeah, Rami? Sure. No problem. Okay. If that's it for questions, we'll go ahead and move on to section A3. So in section A3, we're going to talk about solving systems algebraically. As we saw last time, even though we have this method of solving systems graphically, and the graphical method works just fine, it's a little bit tedious because things like neatness count kind of takes up a lot of space. It requires really, to do a good job, a digital resource. It's very difficult to, like, if you had an answer that has 2 or 3 decimal places in it, it's very hard to do that kind of thing by hand and get that accurate of an answer out of it. And then when things really start to fall apart is if we have bigger systems that have 2 or have 3 or 4 or 5 variables or something in there, where there's not even like a graphical analog to those sorts of things. So now it becomes really kind of troublesome to do this. So we'd really like an algebraic method that's not reliant on generating pictures, and we're going to see 2 of those here today. The first algebraic method we're going to look at is substitution. And again, this should look familiar from what you did last year in your Algebra 2 class. We're largely just kind of rehashing things that we had done. So we'll talk about the steps that we'll use to do substitution. We'll do some examples here. So the first thing we're going to do is we're going to choose an equation. And then we'll choose a variable in that equation. And we'll solve for that variable, basically get that variable by itself. So that's our first step. In the second step, and maybe I'll say this then is creates a new equation. So our next step, we're going to substitute our new equation into the other equation. By doing that, we're going to only have one variable type in that other equation now after we do this substitution. So we then solve for the remaining variable. And then our last piece is use our previous maybe I should say substitute our previous answer into one of the other equations. To solve for the next variable. And we would just kind of keep repeating that process over and over again until kind of we have everything solved for. So let's just kind of roll through an example here. So let's say that we want to solve the system 2x plus 5y equals negative 5 and x plus 3y equals 3. So my first step is to choose an equation and choose a variable to get by itself. Now, what we choose here doesn't really matter, but we can make our life easier by choosing wisely, in this case at least. Which equation and which variable would I choose if I wanted to make my life as easy as possible? What do you guys think? The bottom equation, okay, and which variable? Yeah, so that's right. So I would choose to get this x by itself. And the reason I would make that decision is because at no point do I have to do any division. So I know that I'm not going to generate any fractions at any point. And if I can avoid having to deal with any fractions, I would prefer to do that. Now, it doesn't mean that if I get a fraction, I've done something wrong, or that it means that it's not going to be correct at the end, or I've made a mistake, or anything like that. It just, if I can avoid them, I would. If I run into them and I just have to deal with them, sometimes you just have to deal with them. But in general, I think that I would prefer not. So to get the x by itself, all I do is subtract 3y from both sides. Now what I'm going to do is I know that x is equal to negative 3y plus 3. So I'm going to substitute into the first equation now x, and in place of x, I'm going to write negative 3y plus 3. So I'm going to start by just recopying the entire first equation, but in place of where the x is, I'm just going to write negative 3y plus 3. Notice after doing that, the equation that I now have only has y variables in it. I have no more x's. Since I have only one kind of variable in my equation, I can now solve for that variable. So I'll start just by distributing the 2 through, giving me negative 6y plus 6 plus 5y equals negative 5. I'll then add the negative 6y and then 5y to get negative y. I'll subtract 6 from both sides and then divide by negative 1. Now that I have the answer for one of my variables, I can solve for the next variable by just going and plugging this back into some previous equation. So I could plug in to this equation, or this equation. If it's me personally, I would use this one. The reason that is because the x is already by itself, so it saves me just a little bit of algebra. Not a lot, but just a little bit. So again, in substituting, all I'm going to do is just rewrite the equation exactly as it is, but in place of the y this time, I'm going to write 11. So negative 3 times 11 is negative 33, and then I still have the plus 3. When I combine like terms, I get negative 30. So when I put these two together, I'd get the answer, which is the point negative 30, comma 11. Feel okay to you guys? Okay. So I think the natural next question is, okay, Mr. Kulik, so if there's one solution, I get how that's going to go. What if we run into one of those other situations where we have infinitely many solutions or no solution? How's that going to work if I do this substitution? What's going to end up happening along the way to tell me that's what's going on? Well, let's look at an example then. So let's say we have 4x minus 6y equals 8, and 2x minus 3y equals 5. And we're going to solve this system here. So in this situation, no matter which variable or which equation I choose or which variable I solve for, I'm going to end up with a fraction, right? It's unavoidable in this situation, and that's fine. To me, it looks a little bit easier if I take the second equation, I solve for x, mostly because when I do that, I'm going to get denominators of 2. But when I plug that back into the second equation, every coefficient in there is even, so the fraction will just kind of go away. You might notice that, you might not. It doesn't, again, you might have to deal with some fractions for a little while. It's not the end of the world. But that would be what I'm seeing to motivate the choice that I'm making, and just be like, oh, I can save myself a little bit of hassle if I choose to do that. So now I'm going to substitute the x into that first equation. I distribute the 4 through. After I do that, I have 6y plus 10 minus 6y equals 8. If I combine the positive 6y and the negative 6y, those just are going to cancel out. And I'm left with 10 is equal to 8. Is that right? No. So if I'm left here with a false statement, that's going to tell me this is no solution. What would a infinitely many solution situation look like? It would be something like you'd be left with 10 equals 10, or some kind of true statement. That would be what would imply the infinitely many situations. Everybody's okay with that? Okay. Our next method that we're going to talk about is the elimination method. And personally, this is the one that I prefer to use. I think it's the easier one to use, mostly because you can avoid seeing fractions a lot easier doing elimination than we can substitution. Some substitution problems you run into fractions, there's just no way around it. In elimination, you can avoid seeing fractions until your very final answer, if you really are being careful and making choices to not intentionally making fractions for yourself. It's nice like that. So let's just kind of outline the process here. Again, elimination is something that we looked at last year in our Algebra 2 class, but let's rehash it because it's been a little bit. So the first step is to choose a variable to eliminate. And then we multiply one or more equations by a number or numbers such that the variable to be eliminated has opposite signs in two equations. I shouldn't say we shouldn't say opposite sign, we should say opposite coefficients. So when I say opposite coefficients, I mean something like 3x and negative 3x would be opposite coefficients. Everybody's cool with what I mean by opposite coefficients? Again, you probably were without even the example, but again, it's been a little while. That's what review is for, right? We go back and we just tell you stuff you already know. Okay, the next thing we do is we add the equations. This eliminates one or more variables. And creates a new equation. We then solve the new equation. And then we use that answer to substitute into a previous equation to get the rest of our answers. So let's do a couple of examples here. So let's say we have the system 3x minus 7y equals 10, and 6x minus 8y, or 8y equals 8. I'm going to refer to these equations as equation A and equation B, just so that when I make some notation about what it is that I'm doing, it's a little bit easier to illustrate that. Okay, so let's say I want to eliminate the x. So what would I have to multiply equation A by, or equation B by, or both equations, so that the coefficients on the x are opposites? Jay? Great. So I can do negative 2 times A, and then if I add that to B, the x's will cancel out. Let's say instead we had chosen to eliminate the y's. What would I do there to eliminate the y's? Well, unlike the x's where the coefficients were 6 and 3, it was easy to see the least common multiple of 3 and 6 is just 6. The least common multiple of 7 and 8 has to just be 7 times 8, or 56. So I could so what could I do then? Jay? Very good. Or similarly, I could use positive 8 for equation A and negative 7 for equation B. Either one would be okay. Now, given these three choices, which one of them seems like the easiest thing to do? The first one, right? Everybody is agree with that because we only have to multiply one equation. That's what I would choose to do here, but again, it doesn't matter which one you do. I just usually try to find the thing that's like the simplest. All right, so the equation negative 2 times A, negative 2 times 3 is negative 6. Negative 2 times 7 is positive 14. And negative 2 times 20 is negative 2 times 10 is negative 20. And the equation B, I'm not changing at all. So I'm just going to line those guys up and then add straight down. Negative 6x and positive 6x, just when you add them together, you get nothing. I'm not going to bother to write the 0 there. You could if you wanted to. I'm not going to. And then positive 14y and negative 8y gives me 6y. And then the last step here, negative 20 plus 8 is negative 12. When I divide both sides by 6, I get y equals negative 2. And now I'm going to go back and plug in that y equals negative 2 to any of these previous equations. So I could plug it in here, or here, or here, or here. Any of them is fine. Personally, I would probably plug it back into equation A, just because the coefficients are the smallest there, and it's To me, smaller numbers are usually preferable, but it doesn't really matter. So if I am going to plug y equals -2 into equation A, so that's just like a little silly notation for me to write down so I know what I did. So 3x minus 7 times -2 equals 10. So again, all I did was replace the y in equation A with -2. -7 times -2 is positive 14. I subtract 14 from both sides and then divide by 3. And I'll get -4/3. And if I put those two together, then there's my solution. Everybody's okay with that? Again, if I do one of these eliminations and I get something here that's like 0 equals 1, that's no solution, or like 0 equals 0, that's infinitely many solutions. Everybody's okay with that? However, x equals 0 is fine. That's an answer, right? You just keep going with the way we just did that. I want to make sure that we're clear that the variables can equal 0 and it's no problem. It's if you have no variables left, that's when you're either going to run into an infinitely many or a no solution situation. Okay? So just again, addressing that situation without doing an example, because really it's the same thing, right? Okay. I have one more thing that I want to talk about here. And what I want to do is another example of like a story problem. So remember last time we did a story problem example where we had to like decode what was going on and come up with our own equations and everything. You guys remember doing that? Yes, good. Oh, what the heck? All right, whatever. Guess I can't do it that way. Let's look at another example of that, right? Because that's not easy. It's probably the hardest thing that we've done so far. So let's just kind of go back and look at it and do a little bit more practice about doing that decoding, right? Those of you that are juniors or maybe seniors still that plan on taking an ACT relatively soon, this is a skill that pops up a lot where we're given a story problem, we have to decode it into an equation. It's a favorite of ACT type questions because you can't like just plug it in your calculator and kind of guess and check it, you know? So let's look at an example here. So to raise money for new football uniforms, you decide to sell t-shirts. The short sleeve t-shirts cost $5 and you can sell them for $8. Long sleeve t-shirts cost $7 and sell for $12. If you spent $2,500 on t-shirts and sold all of them for $4,200, how many short sleeve t-shirts did you sell? Oops, I guess I didn't. How many? So the first thing we'd want to do in this situation is determine what are our variable or variables. Everybody okay with that? So typically in a story problem, the last sentence is going to give you an idea of at least what some of that is, because it's going to be asking a question, and typically whatever you're looking for is one of your variables, right? Okay. So in this case, what is one of our variables? Landon? Yeah. So I'm going to use the letter S to represent that. And I'm just going to call that the number of short sleeve t-shirts, because in the problem it says that everything, all the t-shirts we bought, we also sold all of them. So there's no difference. It's just short sleeve t-shirts is short sleeve t-shirts. Now there's actually a second variable in here that's not expressly asked for, but you can probably infer it pretty quickly from the context of the question. Landon? Well, we know the cost, right? That's $5 per shirt. So let's think about what's going on, right? So we've gone out and we've bought some short sleeve t-shirts, and we buy some long sleeve t-shirts, and that we spent $2,500 doing that, right? And then we sold these short sleeve t-shirts and long sleeve t-shirts for a profit, and we sold them for $4,200. Yeah, it's going to be the number of long sleeve t-shirts is the other piece we need, because we need to know that in order to come up with the 2,500 or the 4,200. Everybody's okay with that idea? So I'll use L for the number of long sleeve t-shirts. And again, if we're not really sure, like we just were there, really good practice is to go back and reread the question and make sure you really understand what's going on. And kind of like, okay, to get this number, what would I have needed? Is this number something that's given, or is this number something that I could calculate? And if it's a to calculate number, oftentimes if there's like a variable like L here that wasn't expressly asked for in the question, you can kind of infer it from the other stuff going on. Is everybody okay there? Yes, of course. All right, so we have that. Next thing I'd want to do is to start trying to write down my equations. So I'm going to write these down probably in words before I do them in symbols, though. How would I What kind of two equations would I need to write here? What are these two equations going to be describing? We've already kind of touched on it here when we talked about what was going on. Landon? Not exactly. It's going to be describing how we got these numbers. So how would I have got to the 2,500? Victoria? Yeah, so just the cost of the short sleeves times the number of short sleeves plus the cost of the long sleeve times the number of long sleeves should give us our total cost. Or as Victoria said, 5S plus 7L should equal 2,500. Everybody okay with that? And then we can do the same thing for the revenue, right? So we would just do the price of the short sleeve times the number of short sleeves plus the price of the long sleeve times the number of long sleeves is going to give us our revenue, or the amount that we brought in. So in this case, that would be 8S plus 12L equals 4,200. Everybody feel okay with how we got to here? Okay. So next up is I need to choose a variable to eliminate. Now it doesn't really matter here, but we can make our life a little bit simpler depending on which variable we choose to eliminate. Which variable would we want to eliminate here to make our life the easiest? We'd want to eliminate the L's. Why, though? It seems like either way I do it, I'm going to have to multiply both equations. Why is the L the easier one, Mr. Kulik? Because the question is asking specifically about the number of short sleeve t-shirts. So if we eliminate the L first, we'll get our answer immediately rather than having to, if we eliminate the S's first, that would give us the answer for L, but we'd have to substitute that back in to get S. So it just like saves us a step. Doesn't really matter. Doesn't prevent us from getting the correct answer if we eliminate the S's first, but just makes it a little bit more to do. And, you know, I have enough to do in my day. I'm going to do extra math if I don't have to. You know what I mean? Okay, so if I want to eliminate the L's, what do I do? Landon? Yeah, except instead of just the 7, you really mean the equation A, right? And that, right? We're going to do negative 12 times the first equation, 7 times the second equation, or you flip the negatives doesn't really matter which one you want to make negative. Everybody, you buy that? Again, since 7 and 12 are relatively prime, their least common multiple is just the product of the two of them. That was a lot of words, but you can always do that, right? If you're not sure, like, what number to, like, coefficient to try to make opposite, you can just use, you know, the coefficients of the other one. Anyways, negative 12 times 5 is negative 60. Negative 12 times 74 is negative 84. And negative 12 times 2,500 is too early in the morning for me to reliably think I have that. What is it going to be, like 60,000 or something? 30,000. Oh, yeah, of course. You're dumb. 30,000. Oops. Negative 30,000 because it was negative. And then same thing here. So 7 times 8 is 56. 7 times 12 is 84. 7 times 42 is 9. I don't trust myself. Okay. 29,400. So we add down. Gives us negative 4s. That stuff is just 0. And then negative 600. If I divide both sides by negative 4, I get that, I guess we have 150 short sleeve t-shirts that we bought. What do you guys think? Not bad, right? Let's choose here as a decent place to stop. We're going to add on to our problem set then, 9 through 18. Just as a heads up, you can see up on the board I have kind of the relevant dates for the rest of this chapter. Notice that what we haven't done yet is, for this chapter, homework quiz. What should you expect coming quite quickly? Homework quiz. What should you be worried about for the homework quiz? Well, certainly at least sections 1 and 2, since we've had a chance to go over that homework. Everybody's okay with that? Section 3 that we did today, I would not put on would not call fair game on a homework quiz until we had a chance to go over it, which we haven't done yet. Everybody's cool? Okay. Notice that next week I have chapter tests in mind, right? We have one more section in this chapter, and then we have a review day, and then we have a chapter test. But this one should be okay, right? This is a relatively easy chapter, pretty narrowly focused. There's not a lot of stuff. We're just kind of solving these systems of equations and inequalities. That should be good news for you, right? We like the little narrow chapters that there's not a lot of skills in. They're much easier to prepare for than like a big giant chapter that took a long time to do that has a lot of stuff in it. Plus, by and large, these are skills that we're already probably pretty comfortable with. These are things that we did last year, so that's always a good sign too, right? When we're asking to do stuff that we've already kind of done.